All right, good morning, everybody, or afternoon, depending on when it is for you. Thank you for taking a little bit of time out to get some knowledge around Autodesk HSM 2018. So let's go ahead and step right into this. So the basic agenda that we're going to follow for this is to talk quickly about the benefits of integrated CAM. Then we're going to go through setup, program, and simulate some 2D machine tool paths. Then we'll step over and generate some 3D machine tool paths. Then we will kind of continue on up the dimensional stack, if you will, and look at indexing and pattern operations in the 4th axis, or around the A-axis. And we will also finish up by taking a look at creating some 5-axis toolpaths. So, without any further ado, let's talk about the benefits of integrated CAM. So the why around integrated CAM, comes around having model associativity between the CAD and the CAM, providing a seamless workflow, especially when changes are made to the CAD model. Of course, taking advantage of advanced toolpaths, in particular adaptive clearing, to very quickly remove material and roughing operations. But then also having the 2.5D and 3D tools, 5-axis tools, turning tools, even cutting tools for water jet, laser, and plasma. But of course, having a modern architecture that supports true 64-bit and multi-core, so that we're able to generate and update our toolpaths very quickly. And the ability to inspect generated toolpaths with simulation and verification tools to make sure we're not going to collide with the tools or with the parts in the process of machining as we're moving through the milling process or turning process. So when would we benefit from integrated CAM? One time would be when both design and fabrication is being done in-house, and we have the ability to, or the need to generate those NC programs right inside the tools that we're using to design the products or the components. And when there's no other reason to pay for a separate CAM package, when the integrated CAM package does everything you need it to in that single collection. So how would we take advantage of integrated CAM? You can leverage Inventor HSM, HSM Works, or Fusion 360 in the product design and manufacturing collection. And if you want more information about HSM in particular, you can follow that link there at the bottom. So now that we've kind of identified the benefits of working with it, let's talk a little bit about the 2D milling and turning needs of typical customers that we're talking with. One of the biggest needs is certainly straightforward 2D milling and turning of machine parts, and the ability to have changes that are made to the model, quickly regenerate the tool paths in our CAM program. So what Fusion 360 CAM delivers is robust high-speed machining and turning tool paths and the easy-to-use setup, operation programming, and simulation tools to be able to go through and work with it. And we're going to be moving back and forth or oscillating back and forth between Fusion 360 and Inventor HSM. But the tools are available in each. They're also available in HSM Works for those of you that are using SolidWorks. So let's go ahead and step into the first demo. So here we have a setup, a couple vices. We're doing 2 tops, and then we're flipping them over, doing 2 bottoms to go through and finish off the parts. So as you can see in Fusion 360 right now, we're in the modeling workspace. If we go in and select the drop down, we can switch over to the CAM workspace, and it makes some adjustments there in the browser. and identifies that we have 3 different setups. So we've got just an initial one to kind of show that first setup aspect and do a little bit of milling, and then setup 2 is going to finish out the top, and then setup 3 is going to take a look at the bottom and how we would finish off the part completely. So if we start out in setup 1, as we step into this, we can see we've got our WCS origin identified there in the middle, which isn't quite where we want it. So let's go ahead and edit it. By going into the setup edit dialog, I can go through and use a stock box point to identify where I want to locate that. So I want to go to the innermost corner closest to the inside of the table. And we do have some other options, right? I can use model origin. I can use a selected point, right, in this case on the vise, or model box point if we want to go right off of the model as opposed to the stock. Another nice option is if I happen to be doing some tombstone machining and actually need to reorient my Z-axis, I have the ability to go in and just pick a face I want to be normal to, and it'll go in and adjust those automatically, right? And if I don't need to do that or need to, flip that around, it's just a matter of, making a different selection again to get back to that stock box point. So some nice, functionality just with setting up our work coordinate system and identifying where that origin needs to be. Let's go ahead and take a look at being able to adjust the stock itself, right? So we can go off of fixed or relative box sizes, cylinders, tubes, or even from a solid, and we'll take a look at that from solid when we're looking at the bottom. But we want to go in and put some material around our part, and we'll put a little bit of an offset above the top, and we'll go ahead and extend this down so that it, we've got enough to grip onto with regard to filling up our soft jaws appropriately. So now we've got, the final dimensions of the stock identified in there. And if we go over to the post-processor tab, you can see we can identify the program number, right, the comment that goes along with that. And if we needed to, we could even do multiple WCS offsets, right, just going in and specifying what those are going to be, defining the number and the information that goes along with that. So now that we have our stock set up, probably the first operation that we would normally do from a 2D side would be a face operation. So we want to go in and select our facing tool. We do have a pretty substantial tool library that's provided for different materials, both inch and metric, sample holders, probes if we need those, taps for both ANSI and ISO, some turning tools, and we also have the ability to go through and set up our own libraries locally so that if I have 6 machines and each of those machines have different tools in the turret, we can go through and set those up and be able to rely on those and going through and setting up our tool paths or our milling operations instead of trying to remember what do I have or going, forcing the machinist to switch out different tools that are really not necessary. So in this case, we're going to go through and select our face mill, and we'll go ahead and say OK to that. And what is usually a good rule of thumb as you're working through this is, well, let's identify the tool, let's identify the operation, and let's see what the software comes up with regard to the operations. So here we're seeing we're making one pass over, turning around, coming back to clean off the top. So let's go ahead and take a look at what that looks like from a simulation standpoint. Again, just kind of doing a check, understanding what we have, and being able to make some informed decisions with regard to that. So if we go ahead and start playing this, right, we can see that it's just coming down and following the path. If we want to see the stock, we can turn that on and kind of see what it's moving through. So it's taking us down to the height. If we want to speed it up, right, we can speed it up. If we needed to go through and control, move backwards and forwards, and have that update, we're able to do that. But I think as we're looking at this, right, a couple things pop out at me. Number one, maybe we're pulling a bit too much material off of that, in a single pass. So I'd like to do that in multiple depths. But the other thing is I want the tool to come all the way off the part before it comes back, so that we get a nice finish on the top instead of having it, essentially turn on the part. So let's go ahead and edit our facing operation. So we're going to go over here to passes, and we'll identify the offset distance that we want to have. It'll move it far enough to come off the part. And then we're going to do multiple depths, and we'll do this in about 2 steps. So, 50 thousandths each to take off the 10 thousandths on the top. Sounds good to me. And I go through and do that, and you can see that it's, automatically updated the tool path, the preview, where that path is going to go. Shows us it's definitely going to come off the part before it comes back around. It's going to do this in 2 passes. So I'm pretty happy with that as the operation that we want to have for facing this part off. So the next thing we're going to take a look at is 2D adaptive. Let's pick 2D adaptive. So one of the important concepts with regard to HSM is in the title itself, right? So HSM is high-speed machining. We want to do a roughing operation for this, and we want to clear out as much of that material as possible, as quickly as we can. So one of the concepts that goes along with this high-speed machining and the adaptive is to be able to run at the highest speeds and feeds appropriate for the tool and the material that we're running on, right? The tool we're running with, the material that we're cutting. So what we want to do is go through and, optimize the load on the tool. One of the best ways for us to do this is with 2D adaptive, or with our adaptive clearing tools. We've got it for 2D and we've got it for 3D. The benefits of this tool is that it's going to go through and scallop, basically taking the same size cuts every single time as it's going into the material, so that we're not actually burying the tool in the material, and modulating the load on the tool, which tends to, shorten our tool life and cause additional wear and could even cause problems in the part itself, right, and how the part's being machined. So I went in and identified the edges that I want to set up, including a couple open contours for those pockets on the top in between the 2 ends. So we're going to go through and have it clear that out and see what that looks like, just in the calculation that it makes. So we can see that it's going to do a tapered heel down into the pocket. We can also see that continuous load or scalloping that we're having in bringing that information out, right, or cutting that material out. And we can see that it's easily doing the same thing as it mills out those pockets for us. So that looks like a pretty good, right off the bat, good settings with regard to what we're going to have for that initial roughing operation. We can do the same thing for the outside and finish off and all the rest of that. But as far as this particular setup goes, we've pretty well kind of introduced the things that I wanted to introduce. So let's go ahead and move over to the other one, which has everything pretty well done in it, and we'll just kind of step through and take a look at the information that's in here. Let's go ahead and give it a chance to update those paths based on some changes that I had made. So, we've got this, right, facing operation that we did, right, the adaptive pockets, going out and doing the outside, clearing the outside from the stock, gives us an opportunity to go in and even, bring that just below the bottom, so that when we flip it over, we can use the facing operation to clean off the bottom. And then we used, 2D pocket to go in and clean that out, do a finish operation, and same thing, contour for the outside. But then we came in to do the holes, and we did a spot drill, and we did a tap drill, and then we actually did the tap. Now, one of the nice things about HSM is if I have operations that I'm doing, over and over again, I want to spot drill, I want to tap drill to this size, and then I want to tap it, I actually can go through and store that out as a template. So just bring it back in, apply it to new geometry, and it has all of that information in there that we need. So the next thing that we really want to take a look at is, okay, so I've gone through and generated this. How about, posting out the code? So let's go ahead and look at the post processor. So we've got a lot of post processors that come with the product, right? Pretty substantial amount of tools that are already there and available that we can work with. Autodesk, has made the post processors open source, so you have the ability to go in and modify them. If you need to, you can also put in a request to Autodesk. If you don't see yours in there, ask them to go through and update a post processor or configure a post processor for you if that need exists. Then there are some things that we can actually go through and set up, like if we wanted to use G0, right, or use G28 to G53, we have the ability to go through and set those up in the operation itself instead of actually going in and having to integrate those in the post processor, especially if there's something that we're going to be doing, kind of on an arbitrary basis. So if we go ahead and post this out, right, we'll save that out over top of the one that I did earlier. So we can see, some of the initial information, of course, the program number, the description that we had in there, identifying that we want to use, high feed G1 instead of G0, right, the information for the machine that we're working on, again, some of that initial setup, and then you can see each of the operations, right, our facing operation, and how it's moving through the different ones. If we go down here towards the bottom, right, so we can see there's the taps that are happening, for each of the positions, right, the 6 holes that we've got. But we realize, oh, wait a second, or we've got a change that comes in, and we don't need, in this iteration, we don't need the 3-hole version, we need a 5-hole version. So one of the benefits of integrated CAM is the ability to go in and make those changes to the CAD model in the same software you're working on or programming in, and have those updates happen for you. So let's go ahead and switch over to model, and we can see we've got this top that I want to make the change to. So I'm going to go ahead and open that up because it's actually a linked model in Fusion 360. And in here we've got access to the feature tree, so I can go in and edit that feature. And simple modeling change, going from 3 to 5, obviously from a modeling standpoint that's pretty easy to do, but from a programming standpoint, we've now made some significant changes to the overall code that needs to drive this. So I'm going to go ahead and save that out. And then we can go through and step back over into, the milling assembly that we're working with. And you can see now it's identifying that, that component, which is linked, is out of date. So let's go ahead and update the model. So now we've got the updated model, and we can switch back over to CAM. Now, the big thing that we can identify is that it's like, hey, wait a second, there's been a change. But like we did, as I stepped into this, I can just go through and say, all right, go ahead and update those tool paths, and let's see, what we have. So, obviously one of the big ones is the pocket that updated. But you can see that it went in and updated that. We're still going in and using that same continuous or optimized scalloping to go through and clear out, the 5 pointed star now instead of the triangular type shape that we had earlier, right? So that's, very useful and, really pretty quick to have happen. So if we were to go in and say, okay, well, let's go in and repost that. So go into the post tool, overwrite the file that we've got for these new changes. Right, so all that information is updated. Now if we take a look in here, we now have those 10 being identified where before we only had 6. Right, so just that quickly we're able to go in and iterate those changes without having any substantial real effort that's taking. And a lot of other modelers, there's a whole re-import, reprogram process that takes quite a bit of effort. You're basically starting from scratch. So let's go ahead and take a look at clearing this off, the bottom, and finishing off what we need to do for this particular part. So we'll go ahead and let these regenerate. And take a look at a couple things that we were talking about earlier. So in this case, we've milled the top side. So when I put in the stock for the bottom, I actually needed to go in and use a model representation of that. So, we're going to go through and mill this from a body, right? So a stock solid that has been put in and it has the geometry that we would get off the first side, right? We've got the information that goes along with that particular setup. Yeah, it was by going in and saying, hey, I'm making changes to the setup. They wanted to be updated real quick, make sure that everything was still in line. So in this case, let's go ahead and run the simulation so you can see what we're going to do, and we'll kind of talk through that. So in this case, right, we want to see, and you can see the stock that's in there, but we're going to start out with a milling operation again to go through and remove that material. Right, and we'll kind of speed this up. But we're going through and making a couple passes. A couple other things to look at, right? So we've got the info tab where we can see, which operation that we're in and be able to get the, data as we're moving through, the position of that, spindle speed, feed rate. Now we're coming in and, using the adaptive clearing again to clean out that pocket. Come in with a finishing tool. We're going to bore out those holes and then come in and do a finishing, circular operation. And then we'll just come in and spot drill, those holes to really finish out the part. And the nice thing about this is we're moving through it, right? We can see, the statistics for each of those operations. We can see the total time that it takes to mill, this backside. And really kind of understand a lot of the information as part of that simulation. And it also has the ability to stop on collision if we have, times where the tools run into the part or run into the fixture. We can identify those and see exactly what's going on with regard to that. So one of the other nice things that's available as part of this is the ability to generate setup sheets for this particular operation. Kicks it out as an HTML report. So we have that information for what we just saw, setup information, totals as far as tools, number of tools, what the tools are, the values that go along with that, right? And then the individual information about each of the tools, and then each of the operations and the order that we are going to be doing them. Again, saved out as an HTML file that the machinist can pull up on a thin client out on the floor in any HTML browser. So some nice information with regard to that, and I think that pretty well concludes what we're going to talk about with regard to milling. Let's go ahead and jump over and take a quick look at turning. So in turning, right, of course, support of lathe operations or mill turn operations kind of fall within that. So we have our stock setup where we're obviously holding the material, the stock, and then a little bit of an offset. We've already got our work coordinate system set up. So we've got a facing operation coming in to clean off the face. We've got a profile operation, right? Those have already been programmed in. So let's go ahead and finish this out. So I'm going to go in and create a derived operation to do a groove. And we're going to pick the groove tool that I've got. And we want to go through and control so that it's just going to mill out that groove for us. So we'll go through from a selection standpoint and say I want that to be the front, and I want this to be the back of the groove. And we'll go ahead, I need to adjust that down. Doing some checks for me to make sure I have the right values. I don't want my step over to be the same amount of the, for my roughing pass to be the same for the overall. So we take a look at that, and it'll go through and cut that groove for us, which is good. That one looks like it should. So we're also going to go in now, and we want to do a thread. Right, so we're going to identify the thread for the turning, and we'll just grab our thread tool that we've got in there. The geometry of this is going to be this face, and we can go through and control the offset. We'll do like a 2 millimeter lead in and run out to go through and have that smoothly transition in. And we're going to do that in 5 passes for the thread depth that we've got. So we can go through and see that it's going to come at that for 5, and that looks good. And then the last thing we're going to do is to part the part. So you'll notice I've kind of picked at these in different ways, right? The derived operation just in the browser or in the graphics window, and then off the ribbon. So you've got a variety of ways to go in, and of course parting this off, it knows to just come in, go to that backside and be able to work from that perspective. So if we say okay to that, and go through and just do a real quick simulation of this. So we see the stock, and let's go ahead and run that. We're definitely going to speed this up to keep everything moving along. So we've faced off the part. Now we're going to go in and do the profile. And we'll even jump through that a little bit more, advance that up. And coming through, make some finishing passes across there. You can see a couple collisions identified. Let's go in and do the groove. We're going to get a little bit close in that. Then we're going to do the thread. All right, so there's some modifications that need to be made, including that, right, parting off. We got too short of a part for the diameter or parting tool that we've got for the diameter of the stock material. So we need to make some adjustments to that. Again, we could have done stop on collision to see where they are. It also highlights them down here in the, kind of the status screen with regard to which operation you're in, so that you can go in and pick on them and actually see what's going on. What is the error that's coming into that. So it's kind of a quick overview of 2D in general, right? So kind of a quick review of what we just took a look at, right? Milling box setup, facing operations. We looked at simulate, again, to kind of see what we have and then make some adjustments. 2D adaptive for roughing, right, with an optimal tool load, high-speed machining. 2D pocket, 2D contour to go through, do some cleanup. The ability to save off templates, generating our tool paths, and doing a groove, doing a thread, parting off a turned part, and the ability to do setup sheets, right? So pretty substantial amount in that, which is why we spent the time. And really a lot of that, the setup, the post-processor, the setup sheets applies whether we're doing 2D milling, turning, or any of the other ones we're about to take a look at. Speaking of which, let's talk about 3D milling and kind of the containment aspect. So really, from a 3D milling standpoint, the customer needs our high-speed removal of material on 3D parts with the optimal tool load. You may hear some catchphrases there and already know where I'm going with that. Precise machining operations that contain the tool to specific areas of the 3D part. Right, so because we're moving in 3D, where 2D we're kind of identifying edges, right, or loops to go through and follow. In 3D, obviously we've got the third dimension to worry about. So really it's just more about tool containment so that I get the finished product that I'm expecting. So we're going to jump over to Inventor HSM for this one, but Inventor HSM delivers our 3D adaptive clearing, just like we have the 2D, same benefits, you know, but in a 3D space, and containment operations for precise toolpaths. So let's see what that looks like. Let's go into Inventor. So here we have our 3D part, and we already have some of this set up, right? So just the normal block we're starting with. We're coming in with a bullnose to go through and clear out a fair amount of material, a 10mm bullnose. Then we come in with a pocket operation to go through and do some more roughing, but in a little bit closer. So we're using a 6mm bullnose to go through and clear that out a little bit better. But then we came in and we did a contour and a scallop to go through and kind of get down in there using a smaller ball end mill. And we're actually going through and using two different operations, right? Contour following around, kind of moving from the top down around each of the humps that we've got on either side of this, and then a scallop to go through and get kind of clear off the top, real nice and even. But what I want you to notice in here is that we're using some settings in the tool itself to go through and do some containment. That contour isn't going all the way up. It could with the default settings, but we have the ability to go through here and identify slope. So we're only going, or we're focusing on from 90 to 60-degree slope for the contour. And then for the scallop, we're going in and going from 0 to 65. We want a little bit of an overlap, right, so that it goes through and handles that appropriately. But being able to go through and control that, right, again, contain the tool to those particular areas. So let's say that we've gone through and we've done a lot of this roughing. We've done some of the, the finer, not finishing, but kind of the intermediate steps. So the next thing we want to do is to do a scallop pass that really kind of goes across the whole component. So we're using a ball end mill to go through and do that. Let's go to the smaller ball, and we want to grab that out of our library. Right, so we've identified that smaller ball, and the geometry it's going to pick up automatically, so we want to make a couple adjustments to some of the pass settings that we have in here. We want to go from the inside out. We do want to control our step over and have stock to leave. And we'll go ahead and drop that down some, right, 0.5 millimeter, sorry, 50 thousandths of a millimeter. So again, just kind of getting in there and giving it an opportunity to move over that, trying to get us, to a point where we've got some nice finishing geometry, getting toward that finished component. So we go ahead and say okay to let that generate the toolpath and see what it comes up with. We'll see that we've got this nice, kind of consistent and just moving over, the entire part, leaving a consistent amount of material for the things that haven't been cleared out yet. So getting that kind of to a point where, now we want to focus on finishing, a couple things. In particular, I want to go through and focus on the horizontal, bed, if you will, that this sits on. So I'm going to go in and use the horizontal operation, and it allows us to contain that to the specific location. We'll use the 6mm bullnose to go through and generate that. And the geometry, we want to go through and actually with a height, we're going to go through and control the top height. So instead of the stock top, I actually want it to be constrained below the fillet, right? So it's really just going to focus on that bed and be able to go through and make the adjustments that we need to. So we'll go through and adjust our tolerance, and let's see, and our smoothing deviation. We'll go ahead and set that up to 1 millimeter for this one. And again, we want to pretty much finish off that bottom, so we're not going to leave any stock on that. And we'll see what this comes up with. All right, so you can see that it's identified, you know, the tool paths around that horizontal area, which is good for a cleanup there. And then the last thing we're going to take a look at, we would still have some finishing operations to do on the top, but focusing in on the fillets. So one of our other constrainment tools from a 3D standpoint is pencil. Right, so pencil is going to be focused on just the fillet areas. So we're going to use, not the bull nose in this case, we want to go back to the ball. And again, you know, go through and make a couple adjustments to our settings, one of which is over thickness. And the over thickness, you know, and really kind of the beauty of all of these is that when we aren't exactly sure, well, what does that term mean? Right, we just hover in it, it shows us, okay, over thickness is applying an additional thickness to the tool to detect passes, right? And that amount is the difference between the actual part radius and the tool radius, so we can go through and make those adjustments appropriately. And then we also want to go through and, you know, manage this with regard to step overs. So we want 5 step overs. In this case, we're going to go 1/3 of a millimeter, right, or 300,000ths of a millimeter to identify the step over for the ball end mill that we're using. So we go through and take a look at what that comes up with a tool path. What you'll notice is that it is definitely constrained that based on the operation just to those filleted edges along the bottom. Right, so we go through and do the horizontal, then we do the fillets, and then you know, maybe come in and do the rest of this with a finishing pass, you know, tight step over, and be able to control those. So again, we've got some nice tools from a 3D side to be able to go through and manage that aspect of it. Let's go ahead and kind of review what we just talked about there. So for 3D milling and containment, right, we saw, you know, what it looked like, tool paths for the 3D adaptive, again, being able to clear that material out very quickly, optimize the tool paths, or optimize the tool load. 3D pocket, contour, scallop, horizontal, pencil, all constraining, you know, to the geometry that we have. Some other related capabilities that are really going to define, you know, how is the tool moving around over the part. So parallel, moving in parallel motion. So again, depending on how, you know, you're moving over the grain of the material, or, you know, what the finish needs to look like. Radial, you're going from the, you know, outside to the center and back out. Spiral, we're spiraling around, you know, kind of like a helical spiral around, you know, the outside into the center, from the center out. But again, being able to control, you know, what we want or need with regard to finish, and containing those tools to, you know, those particular operations. All right, so the next thing we're going to talk about is our 4th axis indexing and some patterning that goes along with it. So the customer need here is a need to precisely orient parts for machining around the A-axis, right, the X-axis of the model, so being able to rotate around that. We also have a need for patterning, you know, our operations, right, or patterning the tool to repeat the operation instead of reprogramming it. Obviously, you can see in this part we've got here that there's a lot of the same operation happening at different angles around the cylinder. But we also can use this supporting tombstone machining, and where we're going in and setting that part up, and we have it on a rotary table and are doing one operation, and then we'll rotate it 90 degrees, do another operation, again, being able to go through and control that. So we're going to jump into Fusion 360 again for this one, but, you know, what HSM provides, wrap tool paths for the machine features around the A-axis, and tool orientation and easy operation patterning options to go through and generate the models that we need. So let's step over into our Fusion 360 and take a look at the part we've got. So we want to start is just looking at the setup real quick. All right, so in this case, we need to go in and make a quick adjustment to where we want our stock point to be. Let's get it to, come on, move over. So you can see rotating around the X, right? We've identified where Z is. The stock for this is just a relative size tube. We've got no offsets. We've got pretty, you know, kind of consistency from the supplier with regard to providing us a, 4-inch OD on the tube itself. So we're pretty happy and able to leverage that without, worrying about it too much. So we can go in like the others and put in our comment that goes along with this. I don't want to call that, how about indexing? I don't know. All right, so again, that goes along with that when we go to post this out. So we've got the geometry in here. If we move this around so that our Z is up, right? Let's say we want to start with this first set of holes, which obviously doesn't match up with Z. So the first operation we want to do here is a drill operation. So let's go out and pick the drill tool, right? And the geometry that we want to have is, this hole right here. But you notice it's not, previewing the path or identifying any of that. Same thing with same diameter. But you'll notice here we've got tool orientation as an option. So I want to go through and set my tool orientation to that hole, right? So it orients my Z. Now it's going in the wrong direction, so let's flip it. That looks a lot better. So you can see where it was starting and now, where it's going to reorient this. So it would rotate that stock around so that it's now, vertically in line with the tool so that it can go through and drill those 5 holes. Of course, we're doing a drill operation, so let's go through and do chip breaking. And then the other thing that we want in this case is to make sure that we go through the bottom. And while the outside diameter has been pretty good, sometimes the less important inner diameter in this case, we want to make sure that we do clear through. So we're actually going to make sure we break through an additional, actually that's a little bit more than we need, 20 thousandths to go through and adjust that appropriately. So it'll drill through those for us, right? Being able to go through, and we can see that just peeks through the bottom to make sure that we've got the full clearance that we want on those holes. Now, again, I said that we've got, that operation needs to be done 5 times. So I could go through and do that again and again and again. But really what I want to do is I just want to pattern it. So if I go in and tell it that I want to add this to a new pattern, not a linear pattern, I need a circular pattern, which means I've got to go around an axis, right? And you can see there's a kind of a preview of the second one below, but I really want 5 total, right? So I can go in and adjust that to 5. Again, we can see that those now line up the way we want them to, and it's now created that circular pattern, and it's put that chip breaking drill operation in underneath it and given us, an ability to leverage what we've already created very quickly and easily. So the next thing we want to take a look at is going in and milling out this pocket. So we're going to use our on-a-face operation. We're going to use our 2D adaptive clearing to go through and clear out that pocket. So in this case, the geometry that we want to select is this inner, that inside edge. And it's not allowing me to pick it up because it doesn't know that we're going to be doing this, curvature. So what we want to do is tell it that we want to wrap the toolpath and just identify the cylinder that we're going to wrap around. And now when we go to select that edge, it goes in and picks up that edge, beautifully for us. So a couple things to keep in mind with regard to this, depending on how you've modeled the geometry, you may have a little bit of kerf material left in this, as we're moving around, because if we're following, this edge with the tool, but we didn't model with that tool offset in mind, we may end up with a little bit of material up here on the top. So depending on which is more important as far as the critical dimension, do we want the top with some extra material removed from the inside, or do we want the inner diameter with a little bit more material left on the outside? We have the ability to go through and control that. So we'll go ahead and get that created along the top. Checking to make sure I've got everything in there. I think that works. So we'll go ahead and accept that. Oh, yeah, sorry, need the tool. Use the roughing tool to do that. But it goes through and identifies the information that goes along with our model. So we've got a roughing operation, and now we want to go through and clear that out, right? We want to finish it out and actually break through. So we'll come in and do a derived pocket operation off of that one, which is, by default going to use the same tool. We're actually going to switch over to a finishing end mill with more flutes, different speeds and feeds. You can see that the geometry is set up for the same, which is good. In this case, like we did with the drill, we want to blow through on the heights, so we're going to go in and put in a similar offset there to go through 20 thousandths to make sure that we mill that all out that we need to. And the other thing we're going to do, instead of helicking into this, we're going to plunge in, because we've already removed a lot of that material, to be able to go through and get that set up. And maybe that was the issue. So we want to make sure that we don't have any stock to leave, so it's going to remove all of that for us in that operation. So let's go ahead and see what it comes up with for that. So now we've got the circular pattern, right? And I want to move those two operations into it. So I can just drag and drop them, and it puts those all in, right? So now we've got the drill, and then the adaptive clearing, and then the pocket, but it's being done, right, on all 5 areas for this as we index around. The last thing we're going to look at doing is doing the contour around the front of this. So we're going to go ahead and do a 2D contour, and we're going to use the finishing end mill for that. Again, like the others, we wrap the toolpath and then go in and select the contour that we want to follow around. Right? So it's going to go through and work with those. Same thing on the heights. So we'll go in and make sure that we've got that set up to a depth, so it's clearing out all that material. Passes are good, entries are good, and I think that should work for that one. So we'll let it generate that. And just to take a quick look, see what is going on here, let's go ahead into the setup, and we're going to simulate that overall process. Those look like good settings to me. So we're coming in and doing this drill operation, and I'm going to go through and kind of move this around to see what we've got. We can see it's drilling through, and we'll kind of speed this up, step through a couple of these. All right, so now it's moving around. Now, the way that this is being simulated, it's showing that the tool's moving around the part, but really the part would be indexed around. Again, you can see it punching through in those cases. And now it's going in, and we're going to speed this up a bit more to move through the rest of this geometry. Right? But it's going in and doing those milling operations or the clearing operations, which really don't show us a whole lot. Right? But now we can see it there. It's clearing out all that material, actually breaking through. The nice thing about doing that roughing operation, leaving some material and then coming back in, and there it's going in and doing the contour. But the nice thing about doing that is that we aren't dropping a big piece, right, or putting any load on there. We're removing most of the material out of the pocket and then coming in with a pocket operation and just cleaning up, a couple thousandths, 10 thousandths of material, to go through and clean up this overall part. So I think as a whole, again, looking pretty good as far as that goes. Let's go ahead and just kind of review or summarize what we took a look at. All right, so we looked at a tube setup this time, but we did a drill operation where we're setting the tool orientation, 2D adaptive and 2D contour where we're wrapping the tool path, and 2D pocket was in there as well. Circular pattern, right, to go in and pattern that around. Some other related capabilities, we have linear, mirror, and duplicate patterns that can be done if we had geometry that, again, fit those particular occurrences. So again, some nice variety for that. Again, support for tombstoning in this, same kind of manner. So the last thing that we're going to talk about here is our 5-axis toolpaths. So the customer need is simultaneous multi-axis motion in the X, Y, and Z, as well as rotation around the B and C axes, right? Rotation around the Y and Z. And another need is the ability to take advantage of full tool edge or swarf machining to go through and mill the component, down using the long edge of the tool instead of just having to work on the tip. Inventor HSM, so we'll jump back to that, provides multi-axis contour machining and swarf machining, as the 5-axis capabilities, and then we have some options in our 3-axis that we're going to take a look at that help us do 5-axis machining. All right, so over to Inventor. Let's close down that one and take a look at what we've got here. So, basically we're getting this part out, right? It's a casting or whatever to go through and give us the general shape, and then we're going to do some final machining to get down to the finished size that we need. So, one of the things that you consider is doing just a 3D contour coming around, the edges of this to go through and move that in 3 dimensions. The challenge that we run into with that 3D contour is that when we, get in and, get down about, to the tool length, so if I go in and simulate this, and just kind of show, right? So we've, got the tool, and of course we want a shorter tool so we don't get a lot of, chatter at the tip of the ball end mill. But as, we get down about a couple inches, right, we're going to start colliding, the shaft with the tool itself, right? So that doesn't work really well. But we do have the ability when we're going in and defining these to actually go through and look at the ability to do, shaft holder and actually check for that. The challenge that we run into when we look at that toolpath is it's trimming the toolpath, so it's only going as far as it goes before it starts colliding. So that's not really going to solve the challenge because we've still got, 2/3 of this that we need to mill out. So one of the options that works really well in this situation is a multi-axis tilt. So if we go in and look at our contour and we go out here to the passes tab, right, the multi-axis tilting allows us to go through and say, here's the maximum tilt, segment length and the tool axis sweep that I want you to move through to be able to go through and adjust that accordingly. So in doing that, right, it's able to do the full portion of this, and if we go in and look at the simulation of that real quick, right, you can actually see, it's tilted, coming into that, but if we were to jump in, you kind of see that tilt happening, right, whereas if I'm looking at it here, and before I start to get in, it's actually moving through, and just based on where we're at time-wise and everything, I'm going to kind of just show you where that tool is moving through and where that's being positioned to go through and clear out that material to be able to go in and, accomplish what we're trying to do to clear out to that finished diameter that we're looking for. All right, so let's close out of that and talk about this, wavy wing, if you will. So one of the options that we have would be morph spiral to be able to go through in a 3D and move around, but because of again, the tool collision and the fact that in the case of morph spiral, we don't have the ability to do the tilt, at least now we don't, it's going to trim that, right, so that it avoids the collision. So as an alternate to that, if we go in and look at the swarf option, right, so swarf, again, is going to move the part so that it is in line. You can kind of see that preview right up here. We're moving the part so that it's in position so we can use the long edge of the tool along that. In this case, we're going through and we're doing 3 depths, 2 passes to go through and get to that finished geometry without running into the situation where we're overloading the tool too much. So if we go in and actually remove these ones that are really kind of not valid ways to generate the geometry, we can go in and step into the simulation of this, and we'll go ahead and start from the beginning. And again, we'll show the stock, right, and go through and speed this up quite a bit. And we'll actually jump into a couple areas. And this, is actually showing, right, we're tilting the tool and going through and clearing away that material. And I know we're running out of time, so jumping through some of these, but as my machine actually catches up with us, we can see where it's going through and clearing away that material, right? And then when we're doing the swarf cuts, it's now switched over to a different tool, and it's going through and updating the information that goes along with that. I want it to be right there. Come on. Yeah, I think we're just not going to get it to cooperate for the purposes of this demo. But anyway, you guys kind of get the sense, right? We're orienting that tool or the part appropriately to the tool, so it'll go through and follow that along and be able to finish it out. All right, so that didn't show quite as well as I wanted it to, but I think you get the gist. There's kind of what the final looks like when I actually give it time to get through the process. Some of the tools we looked at, right, the ability to leverage 3D contour, the ability to check for shaft and holder awareness, right, so that it's avoiding tool collisions. But the multi-axis tilt really definitely an advantage for us there. Morph spiral, again, in some cases would work really well. In this case, not so much. But that's where we have swarf to come in and be able to do that. Multi-axis contour to go through and do some engraving or whatever along, a multi-dimensional profile or surface that we wanted to go through and etch some geometry in would be another capability that we have. So, in summary for this, benefits of integrated CAM, we took a look at that, right, being able to go through and have the updates and again, work between the design and fabrication. But then set up, program, and simulating 2D machine toolpaths, generating our 3D machine toolpaths, indexing and patterning operations for the 4th axis, including support for tombstoning, and creating our 5-axis toolpaths. And I think with that, Cassie, I'm going to turn it back over to you.